Okay, thank you, Rich, and thanks so much for the invitation to talk here. This is actually really a great honor. I've been working off and on for close to 20 years on emotion perception. Here's a little picture of my lab. Expressing a particular emotion. And the way that I've been going about things is to try to understand how people communicate emotion to each other, with the idea that if we're going to measure something about emotion, what we're going to measure is what is expressed. You know, it's either self-report or it's somebody seeing someone else expressing something and then they report. So it has to do with communication. So I really am going to focus on communication here and the words that we use to describe emotion. So the words that we use to describe emotion, okay, I'll keep going. The words that we use to describe emotion may have some structure to them, and there's some well-known ways of going about trying to understand that structure. So the idea is that we produce either in motor actions of some sort and perceive auditory or visual stimuli, and then somehow something happens. And during that something happening, that's what we would really like to understand. But something happens, and then a motor action is produced by the person who's in the conversation. So we have one person in a conversation, they hear or perceive something somehow, they integrate it, and then they produce something. And this back and forth of conversation is the way that we communicate emotions to each other. I'm going to be focusing primarily on facial expressions here. So here's some data from the early 2000s. This is motion tracking data, and these are called windowed cross correlations, these heat plots. And if the same thing is happening all the time, you'll see horizontal stripes on this graph. And if a person or two people here, these are two people dancing, and their head movements across the dance. Here are two people talking to each other. And when people talk to each other, things change very rapidly. So let's take a closer look at this. What I would like to understand, as much as anything else, is how do we construct a shared space between us as we talk to each other? That is, how can we communicate information about the interior states? And the idea is that there may be some points in this, some short periods during the conversation, when much the same thing is happening. So you can see in these blue areas, the correlation that there is a stripe for just a little while, but then there's another stripe down here. What that means is first one person was leading and the other person was following, and then we switched leads and follows. Now the person B is leading and person A is following. And the points where these periods of coordination end, I'm calling symmetry breaks. So this would be what I would call symmetry formation and symmetry breaking. It happens at irregular intervals. We've seen this in lots of data. It happens at irregular intervals. There is some fractal structure to it. You can ask me questions about things that I'm going to throw a lot of words out here, and some of them you may have heard a little bit about, but I can't stop to explain everything because I'm trying to put 20 years worth of work into 20 minutes. So I would like to understand how we form this symmetry, and during that symmetry, that's when the emotion or the information is being acknowledged back and forth between two people. And the symmetry break is when new information is added into the conversation. So this dynamics of conversation is a complex system. It's non-stationary. We can't use normal time series methods to get at this because it is so non-stationary. In order to be able to understand this kind of system, what we have to be able to do is find a way to control the environment and then inject something into the system so that we can do A/B type testing. I mean, we're experimentalists after all. And what we've been doing is we've been using a video conference paradigm to do this. I'm going to show you next some floating head here of Tim Brick, who used to be at my lab, graduate student in my lab, and now he's an assistant professor at Penn State. But let's have him explain it to us.
This is not my face. Well, this is my face, but as it is being reconstructed by a high-presence, low-bandwidth video conferencing system. A single standard web camera records my face. The system then fits an active appearance model to each frame and extracts the model parameters as well as the location of my face.
So the first half of that was actually computer regenerated. It was not Tim. That was a computer graphic. And yet, we are fooled by this. We shouldn't be fooled by this because this is about 12 numbers. 12 numbers for each frame of video. Instead of, a normal frame of video has just a little less than 1 million pixels. This is just crazy, in terms of how much compression is happening. What we're thinking in my lab, or at least what I'm thinking, other people do think I'm crazy, but what I'm thinking is that the reason that people are fooled by this kind of linear decomposition of people's faces move in correlated ways, and the brain tends to use correlated information in the environment to construct spaces that are low dimensional and simpler than the spaces of the information out in the real world. And why do I think this? Well, we had this example, this dimensional example of color before. I'd like to go a little bit deeper into that. What's coming out of the sun is a whole high dimensional, that is to say, lots of spectral bands are white light, what we would call white light. Well, then that falls on something, is reflected back off, and we see then, what's called a reflectance spectrum. This is still a very high dimensional spectrum. If we could see all of those spectral lines, we would be able to tell molecular composition of the carpet and so forth. This is not what we see. Instead, we have 3 rhodopsins in our eye that extract 3 components, essentially, from this high dimensional space. Turns out that if you take principal components or factor analysis of spectral information from the environment, you get 3 components. And not only that, the loadings for the components look very much like the sensitivities of the 3 rhodopsins in the eye. We have evolved principal components for our retinas. We're doing principal components all the time on our retinas. Isn't that amazing? I think we're doing principal components on faces. And that's what we're doing. We're projecting this very complex, system, but it's moving in correlated ways. And it turns out that in our avatars, we can extract 8 to 10 components and get 90% of the variance out of people's faces because we move in correlated ways. And I think the brain is taking advantage of that. The brain is very good at taking advantage of correlations in the environment. Okay, so suppose there is this low dimensional representation. Let's see if we can take semantics, sort of the way that we organize words about emotion, and map it over to that space. So what I did is I extracted 5-second clips, video clips, from, okay, so here, we extracted 5-second video clips from a video conference experiment that I did. Now this video conference experiment, let's see seems like there's a little ring. Could we maybe turn it down a little bit and I'll just go closer? Is that okay? Maybe this other one. Sorry. Okay. All right. That's much better. Okay. So, we have an experiment, a video conference experiment, where we asked two people to talk to each other for about an hour. It was broken up into 2-minute segments. First, one person was asked to describe an emotional memory, describe to this other person that you've never met on this video conference. You don't know where they are. They're out there somewhere in video land, in Skype land. But actually it's not Skype. It's a video booth where they're seeing the other person in real size on a back projection screen with a tiny camera that's just right where between the other person's eyes. So you get this sense of eye contact that you normally don't get with Skype. And people did. So they started to talk. They would describe, person A would describe a time when they were happy. And then we'd ask person B, okay, now you describe a time when you remember being happy. And after about 2 or 3 sessions of this, 2 or 3 back and forth, they are describing really, really intense experiences. It's kind of amazing. They're really talking about, well, and then that reminds me of when my brother died, and it was just devastating. And we're in the control room. We're crying in the control room as these people are talking to each other. It's really quite amazing how much people will express if they're given the opportunity to converse. And this is my first point. I think emotion research has methodologically made a mistake by not studying conversation and instead studying people watching movies. I think that's a mistake. Okay. So we extracted 5-second clips out of these, little thin slices. RAs were told, here's what you should do. You should extract, excuse me, I'm gonna have to look to see and make sure I'm not going too long here. We're going to ask you to take the 2 clips, 2 5-second clips from each person's video that are most expressive. That was the whole instruction, just most expressive. We didn't want to put any kind of theory onto the top of this. We wanted the theory to emerge out of the data. So this resulted in some 750 clips that were, then we did a sort on. We sorted them to try and make them as dissimilar as possible, right? And so some of them became piled up. There's a lot of just, smiles. And so we didn't want to just randomly pick, because there's some of the areas of whatever space of emotion there is out there, some of the areas are overrepresented. So we tried to pick a representative sample or to spread out the stimuli as much as possible by finding stimuli that are as dissimilar as possible from each other. We picked 2 sets of 48 stimuli this way, 48 5-second clips. Then we ran, in the first experiment, we ran 113 people on this paradigm where we asked them, here's a clip, right? And here's the clip that you will see.
Playing volleyball, and it said totally worth it.
Okay, yeah, right. Oh, it worked, right? Now, this is what I'm talking about. People mirror the things that they see. Just the people that were up closest to they're laughing in very, I don't know if you noticed, but they were laughing in a very similar way to this person. And it's kind of a snarky laugh, I'm sorry. So they see the 5-second clip. Our people are raters. naive raters, and then they're asked, they're given a screen. The person in this video felt, and then some emotion adjective. The emotion adjectives came from, 24 of them came from Fontaine and Scherer's work. This is a large web-based questionnaire that was looking for words that back-translated across languages without losing their inter-representational meaning. And we added a few other words to that. You'll see what I mean. We added words that had to do with and this, we ran first the 24, we then added some words. The words we realized that low arousal positive words were basically not in this 24 adjective checklist, so we added some because we thought that they ought to be there. Now maybe that's bad, but that's what we did. The other thing we realized is that there appears to be some kind of ambivalence or masking going on sometimes in our stimuli. It's as if people are wanting to express a socially appropriate emotion, but seem to be actually feeling something else. And once again, this doesn't show up in stimuli that is often used in emotion research. So we added questions about genuine, whether people were hiding, and so forth. Okay, so then you answer this question on a scale of extremely inaccurate to extremely accurate. The idea here is to make some kind of really a unipolar scale, but not just true false, but like true false and several different shades of maybe. And it turns out that people, when we factor analyze their answers, we got very clear results. I don't know if you can see this. I'm going to go and point on one of these. Or maybe I could point with the cursor here so both sides can see. Do you need a telescope in the back to be able to see these numbers? I'm sorry. Just pay attention to which ones are bold. I'll kind of like point you to them. Here's a factor we labeled joy, which has joy, happiness, pleasure, excitement. And these are ordered in order of how much variance are they explaining. So actually the negative emotion did not come out explaining the most variance here. Of course, that might be a function of our stimuli. So anger is the second one that is disgust. Anger, hate, contempt, irritation. These are all loadings of 0.7 and above. Two words didn't work, disappointed and shy, and shy. It's really weird because one of our prompts was disappointed. Tell us a time you felt disappointed. And this did not come out as loading on just a single factor. But we have disguised, that's the third largest factor, is whether the people are masking. Disguised, open, candid, candid, open, disguised, and hid, where two of those are reverse coded. We have a shame factor, shame, embarrassment, guilt, and sadness, just shame, embarrassment, and guilt. We have sadness, which is sadness, despair, and hurt. We have calm, which is calm, relaxed, and peaceful. We have surprised, interested, and compassion. And we call this the interest factor, although you might consider it to be a surprise factor. But this one also is something that is not often you don't often see this come up. We think the reason is because these are people that are talking to each other. And they're either interested in that exchange or they're not interested in that exchange. Maybe you don't see that when you look at Ekman faces or you look at some other stimuli. And finally, anxiety is stress, anxiety, and fear. But I don't know if you noticed, but there are no other loadings above 0.4. It is perfect simple structure all the way down. You don't ever see this. As a factor analyst, you go, oops, I must have made a mistake in the data. It can't possibly be this good. Okay, I'm going to just skip over that because you'll see the same thing happen in a moment. Oh, maybe I should mention, well, why 8 factors? Well, we went through and looked at 4 factors, 5 factors, 6 factors, and so forth. And right at 8 factors, we were still explaining more variance every time, still getting better fit every time. But between 8 and 9 factors, we got to a spot where the 9th factor was just a single item. And that's not really a factor. So we stuck with 8. Okay, so now we did confirmatory factor analysis. We ran the whole experiment again with another 120 people. I think it's, another 120. Oh, the first one was only 106. I misremembered. Second one was 120. And we did a 2-group. So this is just like new stimuli, the second set of 48 stimuli, a new group of people, and we got strong metric invariance. Huh? I'm looking at Rich because you don't ever get strong invariance. That means not only were all of the loadings, we could constrain all the loadings to be the same, but also all the covariances could be between the factors could be constrained to be the same. And with that 56 degrees of freedom, we only lost 25 in fit. And look at the sample size. This is like 1,600 and 1,900. Not easy to do. So once again, we double and triple check this because this kind of result you just don't ever get. I'll skip over this because I have already talked about all of this, except that interest and surprise, now you'll notice that interest ended up having a higher estimated loading than surprise. And that's why we decided to end up naming that factor interest instead of surprise. In the constrained system, the interest factor, or the interest item came up. These are negative. So the other thing that you should know is that this is an oblique rotation. How many people do oblique rotations when you do your factor analyses? Yes, good for you, good for you. Right, you really should be doing oblique rotations. Unless you really absolutely have evidence that factors are uncorrelated in your data, don't force them to be uncorrelated. Let them tell you that they're uncorrelated. Here, it's sensible, for instance, that joy and anger are minus 0.55 correlated. So that's not, like anger and joy, or let's look at sadness and joy. Minus 0.73. That's not minus 1. They are not on opposite sides of the pole. And so they don't collapse to a single factor. They're just highly negatively correlated. So I think this kind of solution is really useful. Okay, so the next piece is mixed emotions. What did people see in these clips? 88 out of the 96 clips significantly predicted scores on at least 2 of the factors. So at least 2 of the factors, that means that they were mixtures of at least 2, and some of them are mixtures of 5 or 6 of them. They're not on these axes. They're out someplace in the middle of the space. In our data, mixed emotions appear to be the norm, not the exception. But we still don't know if these are sequential. I mean, it could be that things are happening really fast. And so we'd like to be able to track things really fast. So what we're doing now, so what we're doing now is we're tracking these things. What we do is we build the avatar model at the bottom, and we put another model up at the top, which has the factors of emotion with the constraint of the intercorrelations that we found in the factor analysis. And now we can go in, take that same clip. Here it is played at half speed. the emotions are shown with the center line here as being a 0 on each of their axes, and it looks like this. We can track the faces, and we're hoping to be able to get to a spot where we can track one every 30th of a second, make a new estimation in an 8-dimensional space. So with that, I'll leave you and say, is this the big 8? I don't know. Thank you.